Hi, and we are back this time to talk about process versus threads. One of the most important features of Java is multi-threading, right? So in this section, we are going to understand a bit more about threads and compare threads with process. As in Java, both terms it's basically very related to each other. We're going to start with talking about what is process, then you're going to talk about what is thread and the difference between each other, and then we're going to talk about concurrence versus parallelism and understand what the difference of those two terms and how that relates to our Java. So then you're going to talk about context switching and what is the implication of this process in our Java applications and how that can impact the performance of our programs. Then we're going to talk about the future of Java, that is basically virtual threads. So, first, what is a Java process? And the answer is very simple. Java process is the Java program in execution. It's basically when you do a Java, you basically run a Java process. In this case here, I'm running our Java application. And this is basically a Java process, right? You can see this process running. So grep, basically from process grep, and you're trying to find Java, right? So, and this our Java application that is running in my machine here. So, and we can also see all Java, not all Java, but all process with this one. So you can see all the process that's running in my application on my laptop, and restricting to Java only, you have those here, right? And we can also see Java application running on our virtual VM. So you can see here, for example, we have IntelliJ, we have Visual VM, and we have our local application running here, right? So process is a new instance of a program in execution, right? So therefore, it has its own space on the memory, and it is not shared between process. So my process here from IntelliJ, for example, is not sharing space in memory with my program that I'm running, right? So this still is sharing my laptop memory, but it's in different space. So one process cannot access the other memory space. Process also follows the idea of parent and child. So basically, where a process can spin up a new process, and the new process will be a child process from the process that started, right? This way, when we stop the parent process, the child process will also be stopped. Let's see how we can stop a process from the terminal, right? So we know that we can stop a process or a program just closing the UI if it has. But in our case, our process that is running here, here we don't have this option to close the program, right? So we have a few options that we are going to explore here, and one of those it's using a command kill. We can basically kill a process passing a signal to this process, and we can, for example, pass sig int and press the number, the process number that we want to kill. So for example, let's to kill this 50866 here, and it might be our process that was running here. So yeah, so we stopped our process, right? So, and how we did that was calling the command kill and pass an event to the process, and then it will be killed, right? So we have a few options to pass a event for a process. So we have this sig hub and sigint that we use to interrupt. It's basically the same we do if we had just let's say started the program here and we just press command C. It's the same. It's the same if we use the sig interrupt. We also have the sig kill and sig term, right? We can kill every process and all the child with this -9 with the sig kill here. Another thing that I would like to share with you, it is that with the ps command and the number of the process, you can see more information about the process itself. So when it started, what's the PID, and the command itself that started the program. But we also can see the tree of this process. If it has any child process under that, it would show here as well. So but we don't have a process that spin up a new process to see as a child process. But be aware that you can see those through this option. Something important to share is when you are killing the process and we are passing a signal, we can get the signal from our application and do a kind of termination to our process, right? So when you on our application here, for example, when you stop the application, we would like to process some background processing. In our case here, we have this trading session shutdown that will log saying that the process is being shut down, and we also start send an event saying that we are finishing the trading day event. We can see that on our, here, let's say we are running our application and we hit the Ctrl+C, all send us a kill signal to the process, and then we can see that we are logging here, shut down the application. So you are able to perform some operation as part of the shutdown process, right? So you see that Spring also start to stop, also has a hook for the shutdown as well, the same way we have here. And this is how we are doing here in our system. So I think that's all for processing, for process, and then we are going to talk about thread. So I believe that everyone that is doing this course already know about what is thread, right? So, but to explain that very simple, thread runs inside a process. So, and as you can see here on our application, we have thread 2 and thread 3 running as part of our program, right? And consequently our process. And the main difference between process and threads when you are conceptualizing it, it's the fact that threads share memory. And that's what you need to be very careful, because when different threads share the same variable, that can be really tricky and completely change the behavior of your program, right? So just to illustrate a bit, let's see if you can see one image here. So yeah, basically we have the processor here, and inside our processor we have memories, like a global variables, right? And every thread is accessing the same variable, and consequently we could say that it's sharing space in memory. And that's what you have to keep in mind when you are developing using concurrence with multiple threads. Another very important concept that we need to have in mind when you work with threads, it's the difference between concurrence versus parallelism, right? So concurrence, it's when two or more tasks or threads can start, run, and complete in an overlap time period. It doesn't necessarily mean that the threads are working in the same time or in the same instant, right? For example, if we are working with multitasking or multithreading on a single core machine, that will definitely not be happening in parallel. But instead, there is a concurrence behind the scene where different threads it's concurring to the single process. So here, for example, to illustrate, we have a queue of people trying to access a vending machine to get a Coke. But we have this one vending machine, but we have many people trying to get Coke from that machine. And therefore there is this queue, and those two queues, it's taking turns to get the Coke from this vending machine. While when we are working in parallelism, it means that it's the first thing, parallelism is only possible when you are working with multi-core process, right? And here to illustrate, you have two queues, and now we have two vending machine, and those two queues, it's working parallel to get Coke. So the guy from the top queue, it's getting Coke from the vending machine, and it's happening in parallel on the bottom queue as well. And that is what is parallelism, when things happening in the same time. And concurrence, we have one single machine, or in our real world it will be a single core, and that the concurrence will be happening to that core process. So tasks are not really running in parallel, or if your computer is not in multi-core, right? Or if you are creating more threads than cores in your machine, and so it's not really working in parallel, right? But what gives this impression that things it's happening in parallel is the fact that CPU doesn't process the thread until from the beginning until the end, but it's keeping changing threads execution depending of the thread state. So basically, when we start a thread, so we create a thread, then we start it, and that thread get the state of a runnable state, and then the processor will get in a queue of processing, and the process pick up that thread. But during the process of that thread, if we have let's say a sleep command, or if we have an IO blocking IO, or you have to wait for a lock, or you have this wait command. All those moment of waiting make that thread unaccessible, let's say not runnable, and therefore the processor will put on a waiting space, and the processor will pick up another thread, right? And will be following this flow of getting new threads and trying to process those, and in the meantime checking if there is sleep time, or if the IO blocking has unblocked, or the lock has unlocked the thread, and other things. And then it would go back to the runnable state, and it will be doing this kind of concurrence for this processing, right? So if the thread it's prioritized, so you can also set the priority of a thread, right? And let's say if the thread is being processed but has any waiting time for wait, the processor will not wait for that to finish, but instead get another thread and try to process another thread and come back when the thread is ready to run again. So that's what gives this impression of being running in parallel, right? So in Java, each thread is mapped to an operation system thread. So think when you are creating threads in Java, Java is transferring this responsibility to the operational system of managing that thread. And when threads alter numbering the CPU cores, so that means you have more threads than the cores, a bunch of CPU time is allocated to schedule the threads on the core, right? So and this process of managing those thread switching is very cost for the CPU, and there is a name for this. If you want to read more about it, it's the context switching, right? And switching from one process to another requires a certain amount of time for doing this whole administration, and saving saving load registers, memory maps, updating various tables and lists under the hood, and all that make this kind of context switching very expensive, and things that you really have to have in mind and try to avoid, right? There is this project from the Java community to add support for virtual threads, and those virtual threads will be scheduled by the Java virtual machine rather than the transfer that's responsible for the operation system, and that would make those threads lighter. And we can see already those this concept of virtual threads present in other languages, Kotlin, Go as well. So, and they call those in Kotlin it's called coroutines, and Go it's called coroutines, and in Java it seems to be called as a virtual threads. And but this is not really available yet, so you can see the name of the project, it's LUM, and it's you can see that there was a change 2 hours ago, so this project is constantly being updated. But we don't have yet which version of Java that will be available. We hope that will be soon, because it's a very important improvement to the language, and having that available will be a big milestone for Java, right? And as I said, the other languages already have that available, and that makes Java be already behind of other language, right? So the takeaway from this lesson is that it's very tempting to thinking that having more threads will spin up things in our process, so make more performatic. But unfortunately, that's not always true, right? Creating too many threads can actually make your application underperforming in some situations, especially if you are running more threads than available core. And hopefully you have learned something valuable about the process and threads, and see you next lecture.